Good evening, dear members. Thank you very much for joining on time. So, as our speaker, distinguished Professor Karu Esselle is also joined now, so we can start the session. First of all, let me give a brief introduction about the session and the way forward. So, once again, welcome you all to the Young Members Section webinar series for the session 2024-2025. This will be our first webinar that we are arranging for this session. And we are absolutely honored and privileged to work with the IEEE Sri Lanka section to arrange this very valuable, informative discussion with the distinguished Professor Karu Esselle. I think most of you all know about his work that he has done in Australia, and it is our absolute pleasure to have him today as the distinguished speaker. Actually, he had a plan to visit Sri Lanka, but for his fortunate, but our unfortunate, he got some government projects, new projects, so he has to work with this project and he has to travel a lot within Australia. So he decided to discuss with you via online platform. So it is absolutely honor and a pleasure to have you sir today. So as per the tradition, let me formally welcome you and then hand over the session to you. So this session is arranging with the support of IEEE Sri Lanka section. So let me welcome them as well. So this will be a live recording at IESL Mysore studio. So a couple of physical participants are also there, and there are a couple of online participants as well. A lot of undergraduates and young engineers as well as engineers who are practicing this field are joining here today. So on behalf of the Institution of Engineers Sri Lanka and the Young Members section and the CEO of IESL, I want to welcome you all for this valuable session. Let me introduce our speaker today to the audience and hand it over the proceedings to him. Karu Esselle is a distinguished professor in electromagnetic and antenna engineering at University of Technology, Sydney. He is Australia's 2022 Professional Engineer of the Year and the leader of the Meta Asterias team that won Australia's National 2023 Eureka Prize for Outstanding Science in Safeguarding Australia, making him the only person to receive both the Eureka Prize and the Professional Engineer of the Year award. This year, he received 2024 Premier's Prize for Leadership in Innovation in New South Wales. Karu is a fellow of the Royal Society of New South Wales, IEEE, and Engineers Australia. His large collection of recent awards include the most prestigious Space Award in Australia, the winner of Winner Excellent Award, as well as the Academic Year Award at the 2022 Australian Space Award, 2022 UTS Chancellor's Medal, and both Excellence Award and the Academic Award of Year at 2021 Australian Defence Industry Award and 2019 Motoshiba Kanda Award for IEEE USA for the most cited paper in IEEE transaction EMC in the past 5 years. Karu has authored over 750 research publications and his papers have been cited around 16,000 times. His H index is 63. Since 2002, his research income is over $33 million. Karu has provided expert assistance to more than a dozen companies in USA, Europe, and Australia. From 2018 to 2020, Karu chaired the Distinguished Lecturer Program Committee of the IEEE Antenna and Propagation Society and has served 8 global committees of IEEE societies. In addition, Karu has been a senior editor of IEEE Access and associate editor of many international journals, including IEEE Transaction and Antenna Propagation, IEEE Antenna and Propagation Magazine, IEEE Access and IET MAP. He was director of YMED Research Center and Associate Dean Higher Degree Research at McQueen University. He has also served as a member of the Dean's Advisory Council and the Division Executive. Karu is a Director of Innovation for Humanity Private Limited. His research articles are posted in many platforms. So it is an absolute honor and pleasure to have you, sir, today. I know it's like 10:30 p.m. at Australia, but still he's very enthusiastic to show his and share his ideas with us. Thank you very much. Without taking much time, let me hand it over the proceedings to distinguished Professor Esselle. Over to you, sir.
Thank you very much, Vismanta, for that very kind introduction. Considering the time, I will let me share my screen. Maybe you have to stop sharing USS.
Yeah, I already stopped, sir.
Okay, yeah, it's getting here. Not PowerPoint. It will hopefully do. Is it coming through?
We can see you, sir.
Oh, good, thank you. So good afternoon or evening for everyone. And first of all, thank you very much for you, Shant, and all the others at IESL and IEEE Sri Lanka for organizing this. Yes, I was and inviting me to give this presentation that was in January, but I'm glad that finally I promised to give this lecture this year, so I'm glad that I'm able to do it, although it was not possible to come to Sri Lanka at this time. Yeah, this will fulfill my commitments to the Sri Lankan community, I think, including this, that is about 12 lectures this year to Sri Lankan community, counting all the lectures I have given at several universities in Sri Lanka, not only in Colombo and Peradeniya, other universities in countryside, Kuliyapitiya, Kilnochi, Badulla, Galle, etc. So considering time, let's get to the topic. I will, to save bandwidth, I'll probably turn off my video and focus on the topic prospects beyond the blue planet space-based opportunities and some associated challenges. So there's a lot of interest in space around the world during this the last maybe 10 years. It's a very large economy, a $1 trillion industry, and there's a lot of investment in this area by major companies like SpaceX in USA, Amazon, and then UK, Europe, like OneWeb, Eutelsat, and so on. A lot of satellites in medium Earth orbit, MEO, and low Earth orbit satellite constellations. With that and the other associated industries, it's becoming a very large growth industry. Hence, there's a lot of interest in all circles, not only in industry, but in academia, in governments, etc., to understand this space economy and space technology. So what I'm going to discuss today is to answer this question, at least partially, what can we do using space-based technologies and the things that we cannot do otherwise without space. I will focus on few areas, more on some than the others: telecommunications, Earth imaging and sensing, position navigation and timing, which is generally known as GPS or GNSS, conducting astronomy from space, and some scientific experiments from space, and some space explorations. Among these, telecommunications is my favorite area, so I will spend more time on that topic. So telecommunications through space or via space. There's the main focus now on telecommunications through space is in high throughput satellite communications, also known as SATCOM, to connect pretty much anyone, anywhere, anytime. That's the idea. With satellites, you can connect anyone, anytime, anywhere. With specific type of satellite constellations. So for example, if you go to a remote area like North Pole and you want to connect with your loved ones or your company or your university, you have no option. The only option is through a satellite. Same with remote areas, remote islands, remote communities in large countries like Australia, Canada. We have communities away from major cities, and they don't have any other means of communication. There's no optical fiber or copper wires, and there's no mobile broadband, 5G or 4G or any G for them to communicate. So the only mode of communication is for these remote communities. That includes their houses, community centers, hospitals, all community facilities is through a satellite. Then ships, including military ships, cruise ships, yachts, and other ships in the ocean. Again, the only mode of communication is through satellite. If you're flying and you want access internet, the only way to get access internet from a aeroplane, business plane or a commercial plane is through satellite. Then in defense, of course, and other transportation systems like trains, coaches, cars traveling in remote areas of countries like Australia, Canada, same. The defense, of course, if you have defense, you are outside your country, it's not safe to communicate with the local network, so they rely on SATCOM to communicate with the headquarters, your own country, other troops. Not only defense, the diplomats and other sensitive officers in other countries to connect with their own country. Often they don't rely on the mobile network or the fiber or copper network, wired network going through another country. Instead, they rely on direct satellite connection with your own country, with your officers in your own country. What happens, like often happens in Australia, if you have floods or fires and other disasters, and all the mobile towers, base stations, all these things are down. A disaster could be natural or man-made, like war. So you lose all the modes of other communications, wired systems like fiber optic or copper, as well as wireless like mobile broadband. And so satellite communication is the last resort. So this is why there's a lot of emphasis in satellite communications in this area, in high throughput communications. The low throughput communications also, there's some interest. Low throughput means low data rate. For example, to connect Internet of Internet of Things, IoT devices using satellite networks. Then you don't need a lot of data, but you want to make everything, the whole system, very extremely low cost. There are companies investing in it. For example, a company called Fleet Space in Adelaide in Australia. They have already launched several satellites to connect Internet of Things. And this is another area that's emerging. Another one, probably you heard, that directly communicating using your handphone through a satellite, like SOS, Save Our Soul type emergency message. For example, you are traveling or has gone to some remote area, say bushwalking, and you're lost and you want to send the message, a short message, but there's no mobile broadband. For example, your GPS location to rescue services. So there's new technology emerging through satellites. That is, I don't believe that will be a high throughput or high data rate, very low data rate, only few bits, but that will be very useful. So for that, some companies like SpaceX are developing something like a mobile base station in a satellite. And so your phone can send a message and receive a message through this service. The standard phone, not a specialized satellite phone. This is using your normal iPhone or Android phone or other smartphone. There are other areas that has been established for a long time. For example, satellite TV is common. It's very low cost technology, well established. And also satellite phones, like Iridium satellite phones, that's mostly for voice only, to connect people in remote areas. And this, we know some of the terrorists use satellite phones. Apparently, even in Sri Lanka those days, because they can bypass the government and directly communicate between themselves through this kind of satellite phones. But that is very established technology. You need a specific phone like Iridium phone to work with Iridium network, but that is not high throughput. Okay, so that is communications area. In other areas, for example, sensing from space, using Earth observation and other satellites is very useful application. For example, if you go to countries like USA, I wanted to check whether there are any bushfires or grass fires in the area. That was in the middle of the summer last year in Portland, Washington state area. I wanted to go for a drive in this beautiful green countryside in northwest USA. So I just Googled to find if there's any bushfires in that area. It went to a website that shows on a map the areas that are hot. So this comes apparently directly from a satellite, from Earth observation satellites. They observe the temperature, and if there's a hot spot, some area that is warmer than usual, then it shows on the map. This is no operator is necessary. No person has to do it. It's all automatic in real time. Straight you see on your phone or computer in internet web page. These areas are unusually hot So that doesn't mean a fire, but it could be a fire. So you can avoid those dangerous. You can, for your own safety, you can avoid those. So that's kind of technology that could that can save lives. And there was a plan in Australia to launch similar satellites, Australian on-Earth observation satellites. Several of them, I think three or four. Unfortunately, that plan was cancelled about 2 years ago. But I hope that it will come back in the near future, because that is very useful technology for countries like Australia. We have regular bushfires and floods in various parts of the country. So the Earth observation satellites can give us all the data we need. Then that can help a lot the emergency services and the residents living on those areas, um, including voluntary fire services, volunteers working for rural fire services, etc. That can save their lives by providing that kind of information ahead of the time about potential danger. Earth observation satellites, some are focused on detecting ships, especially any illegal activities conducted by ships. And normally the ships are required to send a beacon, their ID, but sometimes some don't. That's either they are doing some illegal activity like people smuggling or trespassing someone else's waters, something unusual. So these satellites can detect the ships, and especially those ships and large vessels that are doing potentially illegal activities. And that's also useful for national defense, border security, etc. So all these imaging systems are done using radio frequency radars, for example, using synthetic aperture radars, and sometimes together with some optical methods, cameras. The cameras don't work in the night, cameras in space, and also can't see when there are clouds and bad weather, whereas radio frequency radars can see through bad weather, works day and night. So they are quite useful for sensing from space. This is a picture I got from NASA. I don't think this is a true representation. It's like artistic impression of NASA's Earth observation satellite fleet. The point is they have a very large number of satellites. Some countries have their own satellites that they have full control over. Australia also use some international satellites that are shared with other countries like NOAA. So we do get access to data, but we don't have yet our own imaging satellites, Earth observation satellites. I hope that that will change, hopefully in the future. Now, PNT. Okay, I think this is the most common application of satellites. I guess everyone in the audience have used GPS, right? Normally we call this GPS. The proper name is position, navigation, and timing. Proper technical name is position, navigation, and timing, which is PNT. Helps you to find your position. Through that, help you to navigate, and also it gives timing, very accurate timing information. So out of the PNT system, they are all satellite constellations, satellite networks. The most common one is GPS, Global Positioning Systems. This was developed by USA initially for military use, and then they made most of the signals available to public. Few of them are still restricted. So how does it work? You are sitting here and you want to find out your location. Your GPS receiver looks for GPS satellites. So if you can see about 4 GPS satellites from your location, they can work out the distance. Your receiver can work out the distance from you to each of the satellites, and their location is known. So with minimum 3, but in practice 4 satellites can give you your GPS, your actual location in 3D coordinates X, Y, Z plus timing. But if you can see more satellites, usually you can see more satellites, then you can increase the accuracy, your location accuracy. So that is US system, but the other countries wanted to have their own as well. So many nations launched their own system. So in general, all these things together called GNSS, or Global Navigation Satellite Systems. One of them is American US GPS. There's a European system, there's a Chinese system, there's Indian satellites, and more are coming. So in this area, the normal receivers are very common technology. It is everywhere, mobile phones and many other devices. But the research is on use of multiple frequency bands to improve accuracy using multiple satellite networks. One receiver that can get signals from GPS and the European and Indian and Chinese satellites. For example, a lot of those are visible for countries like Australia. So that is in GPS area. But there's some other very interesting applications also coming up that use GPS signals, but not for PNT, but for other applications. They are in general called signal of opportunity applications, because you're using a signal, in this case GPS signal, for something else, not for PNT, not to find your location, but for something else. So using this signal for you as an opportunity. One of them is passive radar. That is basically a radar, like the synthetic aperture radar I mentioned in the previous slide. But those radars I mentioned in the previous slide needs to transmit radio frequency signals. And then they pick up the reflected signal and use that information for imaging. But in this one, you don't transmit any signal. Actually, you use the signals transmitted by GPS satellites, and you only receive signals reflected by various objects. And then from these objects, and from the knowledge of the locations of GPS that's like using radio telescopes or optical telescopes. And space is fantastic place to do astronomy, because you don't have clouds, right? If you have an optical telescope in space, then whole day you can do astronomy. Then you're not affected by weather changes. So this is one example. This is James Webb Space Telescope, the largest and the most powerful space telescope ever built. And this is run by NASA, and you can Google and find their website and see the images, amazing images. they are all public. That shows what you can do from space in astronomy. There are many other scientific experiments being conducted in space, including ISS, the International Space Station, and then, of course, space exploration, going to Mars, going to Moon, missions to other planets, etc. So I will not explore too much into those areas, but one of them that is close to me is related to moon landing. Neil Armstrong setting the foot on the moon about 50 years ago. On 20th of July 1969, the first humans landed on the moon, and the videos of the first steps and walk were seen around the world live by television. This was the first time a human had stepped on the surface of another heavenly body. Now this is, everybody knows, right? This you can find those images, videos even now, I believe, in internet, YouTube, etc. What most people don't know is those signals, the video clips from the moon to the world, to the TV sets, came through this telescope in Australia. In New South Wales, and another telescope that is close to Canberra in Honeysuckle Creek. So this one is massive, I would say very large radio telescope. So antenna, you can see 64-meter diameter antenna in Parkes, not too far from Sydney in New South Wales. That's actually a radio telescope antenna. It's not a communication antenna, but they reconfigured it to receive signals from the moon on that day. And there's another one, a smaller dish antenna like this, but smaller, 24-meter, in Honeysuckle Creek near Canberra. That was a NASA station. So the plan was to use this or the Parkes, one of those two, when Neil Armstrong is coming out of the capsule and then walking on the moon.
Excuse me, your presentation could not see.
Oh, I see. Okay. I didn't notice that actually. Okay. Okay, is it coming now?
Yes.
So that is, so this is you probably missed Esselle. So this is that 64-meter diameter, very large dish antenna in Parkes, radio Parkes, what we call Parkes radio telescope. So this last year we submitted this as a IEEE milestone to IEEE USA headquarters. We formed a committee. A few people, all were past chairs of IEEE New South Wales, and we were successful, so they approved this as a IEEE milestone. That is actually the first IEEE milestone in Australia. So IEEE milestones are like World Heritage List in science and technology, and for this reason they recognize this as a global milestone. So now if you come to Australia, if you go to parks, you can see the plaque. This was IEEE president last year, and can see the this is the IEEE plaque, and there's Engineers Australia plaque also in the same location. So that is a bit of a history about the telecommunications you can do. That is between space, between moon and Earth, using this kind of advanced, very large antennas. Now have this is for those who are not familiar with satellites. The things were in the satellite, typical things is typical satellite. There are a lot of solar panels. That's how they get power from solar cells. They have lots of antennas for various purposes, data transfer, imaging, command and control, etc. Some of those antennas are like dish antennas, reflected dishes, so they are visible. But some other antennas could be flat panels in the body. They are different and may not be so visible. Then there's a lot of electronic stuff, what we call payload. For example, if in an Earth observation satellite, or the payload could be, a good part of the payload could be the synthetic aperture radar. And then there's a lot of mechanical propulsion system, etc. Those parts I don't know anything about. So this is again from NASA. There's a lot of information in those websites to understand the basic knowledge of satellites. The satellites, when they are talking about satellites, they use some jargon, classification. Most of the satellites that existed for decades are the conventional satellites that are fairly large. They are the most expensive to manufacture and launch. Then the smaller satellites called nano satellites. The smallest one are called CubeSats. They are the smallest and cheapest to make and launch. These are making those and launching is now possible for small companies. Even some universities have launched CubeSats, some experimental CubeSats. For example, some American universities, Australian universities, etc. I don't know whether you get the sound or not, maybe. So this is actual satellite launch. This is SpaceX Falcon 9 rocket launched in December 2018. The actual video from SpaceX. I added this here because this was my first space project, more or less. Making this antenna system, designing this antenna system for this company. This satellite is called Odyssey 1. That's world's first entirely Ka band CubeSat, made by an American company called Odyssey Space. That's a spin-off from Stanford University in California, USA. It's one of the world's top engineering universities, located in Silicon Valley. I visited them. I gave several distinguished lectures, IEEE distinguished lectures at that year, that is 2017, in a lot of countries, and I gave 3 in USA. One of them was in California, in Silicon Valley. I forget, I think it's National Instruments headquarters on Semiconductor Drive. And the antenna engineer in Odyssey 1 attended my lecture and asked me to design an antenna for their first satellite. So my team designed 2 antenna arrays. Not easy to see. This is 1 array and 2 array for transmission and reception for this satellite. We sent the design to USA. They fabricated it in USA and sent us test results. That was pretty good. So they integrated the antenna to the satellite and put the satellite with many other satellites in this Falcon 9 rocket, that is SpaceX rideshare rocket, and that launched, I think, 60 or so satellites in one run, in one go. And that tells something about the rocket technology these days. And actually, it came back after launching. So that's the very interesting part of this. The sad part of that is this Odyssey 1 mission failed after launch. They lost the satellite. So this company, so amazingly creative, entrepreneurial, very ambitious young engineers started this company. They are all graduates from Stanford University, all young engineers. I visited their headquarters. As a very nice, small company type headquarters in Silicon Valley. So still, they failed. They lost the satellite, and they had a lot of assets. They were sold to actually Australian company called EOS Systems. So this concept might come back again, but for the moment, it is on hold. Now that with that, after that, we've done a lot of other projects for various space projects. Most of them are for Australian Department of Defense or other commercials. So I will not say anything about those. But that was a good start. So now more about satellites. Depending on the orbit, there are three types of satellites. One is geostationary orbit satellites called GEO. Those are the conventional satellites. And then medium Earth orbit satellites or MEOs, and then low Earth orbit satellites called LEOs. So these are the most popular, these are the most conventional. The geostationary satellites are in the so-called geostationary orbit or the Clark orbit. Sri Lankan should know who Clark is, right? This orbit is named after Sir Arthur C. Clarke, who figured out that using satellites in the geostationary orbit, we can communicate. In fact, using only 3, you can cover the whole world. For that reason, the orbit was named Clark orbit. So Sir Arthur C. Clarke was the Chancellor of University of Moratua. I believe at the time we were students in the university. Now, what this means is these satellites rotate around the Earth at the same speed the Earth spins, like this. That means relative to Earth, they are stationary. So suppose this is your house, and you are looking at this satellite. So the satellite is always in the same direction from your house. So communicating with those satellites are relatively easy because they are in the same direction always. For example, all satellite TV satellites are geostationary. So to receive satellite TV, all you need is fairly cheap dish antenna permanently fixed to your roof and point it towards the satellite, and that's all. You get the signal with other electronics. You don't have to change the direction. It's always pointing to the same satellite because your dish is rotating at the same angular velocity as the satellite. So I'll get back to geostationary in a moment. But more interesting are the medium Earth orbit and low Earth orbit satellites. For example, most of the CubeSats and modern communication satellites are at low Earth orbits. Even that can change a lot. Most of the Starlink satellites now, I think that most of them currently in orbit are around 400 kilometers above Earth. OneWeb, so this is like a lower LEO, and this is upper LEO. OneWeb Eutelsat satellites are about 1,200 kilometers from Earth's surface, but both of them are low Earth orbit. Medium Earth orbit is higher, and geostationary is 36,000 kilometers from Earth's surface. Okay, so why people are investing on low Earth orbit satellites now? Before that, let's see what is in geo arc, so Arthur's Clarke orbit. This figure is quite old actually. That's we have a date on 2011 or something, so it's quite old, created by Boeing. All the satellites in the geo arc, you can see it's pretty full. So Boeing has 70 of their satellites, those blue ones, and the other companies and organizations have 222. So it's already about almost 300 satellites at that time. There are more now. So these are the companies like Boeing, Intelsat, Inmarsat, Australian Optus have communication satellites in geo arc. Australian NBN satellites, there are 2 of them in geo arc. All satellite TV satellites, as I said before, on geo arc. NBN is quite critical to Australia because especially the rural areas of Australia, because for a long time now they have Starlink and OneWeb access, but for a long time this is the only mode of communication they had, through these 2 NBN satellites, and they didn't have anything else. No mobile broadband, as I said before, no other means. So all communications were through these NBN satellites. Because of the limited number of satellites and the high elevation and various reasons, the capacity of geo satellites are very small, and you have to share it with a lot of people. So getting data throughput per customer is very difficult, high data throughput. Because of the limited number of satellites you can have, you cannot put too many, then you would interfere in other satellites. So then comes the low Earth orbit constellations like OneWeb. OneWeb has about 650 satellites on orbit right now. They are at 1,200 kilometer orbit. And these are not geostationary, as I said before. So if you freeze the Earth as stationary, then OneWeb satellites move around Earth like this, on various orbits. That means if this is the user, this is you. So these dots are satellites. The red dots are gateway stations. I will explain it later. From user, suppose this is you, user, this is your home, and you're trying to connect with the satellite. The satellite is moving above you. So you will see a satellite and it moves, so you have to track the satellite. You have to keep pointing your antenna at the satellite. So again, you can see this is user, this is satellite. You are stationed, but the satellite is moving. So you need to steer the beam of your antenna system, your user terminal, and usually those beams are about 2 to 3 degrees, very narrow pencil beams, to get high signal level, high signal to noise ratio, high data throughput. So with such a small beam, still you need to track accurately and keep pointing at this satellite all the time. And of course, at one point you lose the satellite, it's gone, it's not visible to you anymore. Then you have to find another satellite and communicate with that. So this is how low Earth orbit communication systems work. And this is actual snapshot of Starlink satellites around Indian Ocean. I took this when I was in Colombo. I think, and these are the actual satellites at that moment. It's lots of satellites. 5,500 Starlink satellites are in orbit, maybe more now. That was when I took that. They keep launching satellites because Starlink makes their own satellites. Starlink have the launcher, SpaceX, to launch the satellites, so it's not a challenge for them. And they have plans to launch 12,000 in the near future, and some, according to their plans, people expect that there will be around 40,000 or more Starlink satellites in various orbits eventually. So that's a lot of low Earth orbit satellites just for one company, Starlink. This Elon Musk's a very famous American satellite company. This was the OneWeb constellation around Sri Lanka and Indian Ocean on the same day, about the same time. As you can see, they have fewer satellites. They are going to have only like 600, 700. They are at a different elevation, 1,200 kilometers above us, so it's kind of upper Leo. They don't make their own satellites. Their satellites are made by Airbus, the same French company that is making aeroplanes. Their terminals are made by other companies. And in fact, OneWeb was bought by Eutelsat of Europe. So OneWeb was a UK company. Now it is owned by a bigger European satellite operator called Eutelsat. The point is they have less number of satellites at a different orbit. Then GPS, there are not too many satellites because you need only 4 minimum to get your location. These are some of the satellites, possibly not all of them, I'm not sure, in the same area. And give me a second. And then there are other satellites from other GNSS satellites, as I said before, launched by other countries. Okay, so going back to satellite communication, this figure shows the essential parts of the satellite communication system. So this is your home. This is your SATCOM terminal. Suppose you went to a very remote area, North Pole or remote part of Australia. You don't have any other means of communication. So for all communications, you connect using radio, using your antenna here with the satellite. So this is the user link. This is the user terminal. This is the satellite. So that's uplink and downlink. Data goes up and down through this link. And then how do you get connected with the internet? Then the same satellite in this case is connected through another beam, radio frequency link, with the gateway station that is a larger antenna that is also steering and tracking this satellite, but this is permanently connected to internet, often using optical fiber. So if you send a message or make a WhatsApp call or access internet to anything that needs internet, your data goes to your user terminal to the satellite through the gateway, through internet, and then the cloud and everything else. So that is one way of communicating. But sometimes you cannot have a satellite that is connecting you with the gateway. For example, gateway is here, you are here. So your data has to go through this link, and then between a link between the satellites, that's called inter-satellite link, and then through another satellite, there could be several inter-satellite links and several satellites, and then the final satellite has a gateway, and it goes through the gateway to internet. So this is modern satellite constellations. Some of them are trialing this. For example, SpaceX, optical satellite links, as well as there are proposals on radio frequency satellite links. Actually, we just finished a project on radio frequency inter-satellite links that's funded by Australian Department of Defence through cooperative research center called SmartSat, and we looked into designing antennas and other technologies as a collaborative project with some companies, with other universities, radio frequency inter-satellite links, about antennas and how to steer the beams, etc. And so these are called ground segment, the gateways and user terminal, and this is called space segment. These are mostly satellites and inter-satellite links. So now you can understand this little bit better, the same video. As I said, the first link is the user link. So this is the user terminal, and this is the satellite. So that is the user link. This red one is the gateway. So the red link is the link between the satellite and the gateway. So those are the two radio frequency links I mentioned. There are no inter-satellite links in the OneWeb network, at least not in the current one. It's only the user to satellite and satellite to gateway. Okay, so the challenges in the space segment, that's basically mostly satellites and inter-satellite links to make them low-cost manufacturing and launching, make them lightweight because the launching cost is related to the size of your satellite and the weight of your satellites. You want low power consumption because the good part of the cost of the satellite is due to the solar panels, not because the cost of the solar panel, just because they are large, and their weight and the volume and all those factors. So then solar panels is the only source of energy in these satellites. So you want to consume other parts, you want to have very power efficient, energy efficient parts in the satellite. Sometimes you want multiple beams for multiple links, for example, with multiple users. Normally that's not done. Actually, in most cases you have wide beam to cover all the users, but if you want to connect with multiple satellites, for example, you need multiple beams. You need wide bandwidth to deliver high data rates. There are some other issues like ionization, because ionization level is higher in space. It's especially if it's a geostationary satellite, it has to go, when you're launching, go through highly ionized layers. So some material can get damaged, for example, some dielectrics. So that's another thing to be careful about. In low Earth orbit satellites, at lower orbits, that is lesser issue, but still some radio frequency electronics and other electronics can be affected by errors, data errors, etc. And intersatellite beam steering and multiple beams, as I said before. So those are the areas research and development efforts are focused in these days. The gateway stations, those are very expensive, large stations, so they need large antennas, they're expensive, and you got to install them on land. So land is very expensive in most countries. They need very wide bandwidth, again, lot of traffic, lot of data between the gateway and the satellite. They like to have multiple beams, so one gateway can communicate with multiple satellites. That is not happening at the moment, as far as I know. Usually the gateway antennas are large dish antennas, and they are tilting dish antennas. Because the satellites are moving, low Earth orbit satellites, you need to tilt and rotate the dish to track the satellite. And there are specific bands of operating in the K band, KU band, etc. Some technical details that I can skip. Now to the user terminal. Okay, the main challenge of the user terminals is each user needs a terminal, more or less, so the low cost. Again, wide bandwidth to get the data rate, especially for the downlink. High antenna gain and pencil beam for high throughput. This is not like the Iridium or voice only or low data rate SATCOM, because this may be your only mode of communication if you want to if you need high speed data in your location, then your antenna got to have high gain and a pencil beam. You need to steer the beam. Even if you are stationary, your terminal is stationary, the satellites are moving, so you need beam steering even when the user is stationary. And as I said before, this is a very, very narrow beam, 2 degree or 3 degree beam with pencil beam, so you need to keep pointing very accurately at the satellite. Sometimes you prefer low profile for ease of transformation and installation, for example. There are other modes of operation called communication on the pose or satellite on the pose. That means you move and then you stop when you want to communicate. So where you need to launch your terminal very quickly, rapidly deployable, and communicate, but you don't communicate while you move. So you communicate when you pause. Then there's another mode of communication called communication on the move, communication on the move, COTM, or satellite on the move, SOTM. That means you communicate while you move. So for that, we need really, really sophisticated antenna systems. For example, it could be on top of a roof of a car or a vehicle. So you get satellite communication while you're traveling. So the user terminal has been a big challenge. Even Elon Musk, the Starlink owner, said a while ago, he tweeted saying that his main challenge is not launching thousands of satellites. That he did, right? He already launched many thousands of satellites. rather developing a user antenna terminal for Starlink. So he came up, this was his first trial, the first Starlink antenna, kind of a dish that's tilting. And now, after several generations, he got much better antennas that does not require tilting, and they can communicate with Starlink satellites. Some of them can be even on a boat or a cruise ship or a ship, and still communicate while you move. This is another story from Panasonic Avionics in USA. This is a company that provides provides entertainment in commercial aeroplanes. Panasonic division, but located in USA. Even the Australian Qantas airline used Panasonic systems for in-plane entertainment. They wanted to have in-flight Wi-Fi, internet to planes. So they teamed up with the team in Boeing in USA in 2014 to create a new electronically steered phased array antenna. And their plan was to market it in 2016. So Boeing made a fantastic antenna, fabulous antenna, but the problem was to manufacture them, each antenna cost $1 million US. So even that is low volume price tag, but still it was too expensive. So they gave up at that time. Vice President said this incredibly good antenna, but it's too expensive. So this user terminal has a history of challenges, but now there are better. For example, Starlink, they use a different technology. Instead of gallium arsenide, they went to silicon technologies for radio frequency circuits, and they made several breakthroughs. So now there are better solutions. I think I will go fast now. It is almost 11 o'clock in Australia. So this is a large market, flat panel antenna market. And as you see already, in a lot of these applications, for SATCOM and other applications, you need antennas with steerable beams. So suppose you have a really, really good antenna like this dish, and you want to steer its beam. In the history of antenna technology, that's a century old engineering, there was only one way to steer the beam of any antenna, that was actually mechanically tilt it and rotate it. So you need heavy duty motors and a mechanical system, and you have to change the radio frequency interface with flexible cables, etc., to make that happen. If it is small antenna, it is easier, of course, the smaller gimbal type, but still you have to make modifications, and that was the only method available. But now there's another method that works for any fixed beam antenna, and this is called meta steering. So for example, this blue blocks, so this blue cylinder represent any antenna. It doesn't have to look like that, any antenna with a fixed beam. But using this method, all you need is two meta surfaces. You can see the two discs. Those are thin discs, and we rotate those discs around the axis, and by doing so, this is a representation of the antenna beam. You can change the direction of the antenna beam. If you rotate the disc in the same direction, the antenna beam angle changes like this. There's no change in the vertical plane, it's only in the horizontal plane, that is called azimuth angle of the beam. If you rotate the two metasurfaces in opposite directions, we call it counter rotation. Then the antenna beam, you can see it better here. The azimuth angle does not change, but the elevation angle changes. So we call it elevation scanning. But in practice, we combine both of these. Linear combination of these two allows you to steer your beam from any direction to any direction within a large cone. So this is called meta steering, and main advantage is you don't need to tilt anything. So it is still a flat panel, no tilting. You don't have to change your antenna. You can leave your existing antenna as is. In fact, you don't even have to touch your antenna. You can retrofit these meta surfaces above it, and of course you need the mechanical arrangement to rotate. So that is the only other method now available to steer the beam of any antenna. This method, I invented this method actually in 2016. And we submitted several patent applications, including an international patent application in 2016. I was the lead inventor, and there was another one of my PhD students was the co-inventor. And then we published the method in the top antenna journal in the world in 2017. That's our paper. And I was employed by Macquarie University at that time. So the Macquarie University lodged the patent application, but they did not proceed to the national phase. That means it is not protected. So now anyone can use that method. And I don't get any royalty, or no one, Macquarie University doesn't get any royalty famous. No one has to pay us to use this technology. And a lot of companies in the world and researchers are using this method to steer the beam, because as you can use any antenna you have, you can steer the beam, and you don't have to do any change to the antenna. The antenna is completely stationary. It can be bolted to your vehicle or your house or your roof. Only part that changes are these thin meta surfaces, thin discs, and they can be placed very close to the antenna. So the whole thing is like a flat panel, little bit taller than the antenna, but it can be covered, can be concealed. So it has advantage in defense operations. No one would know there's an antenna on top of this vehicle, or on the side of this vehicle, on the rooftop of this building. It can be totally concealed. So I will skip. This is the optical inspiration of this, called by Raised prism. So this is one of the type of antennas we developed. We also develop other antenna systems. Another way to steer the beam is good old mechanical steering, like the one I mentioned before, like the dish antenna. For that, we used that method actually recently in the project. It's a $1.1 million project funded by Chief Scientist and Engineer Office of the New South Wales government. It's basically the government. So we made these flat panel antennas very thin and ultra wideband, very high gain. The pencil beam 2.5 degrees wide. So this turned out to be the antenna with the widest bandwidth in its class by a factor of 4 or so. And we used it to develop the first ever Australian satellite user terminal. That was for OneWeb. And after that, this was passed to another company for commercialization. We received funding for that project for commercialization. That's about $2.3 million. Half of that coming from the Australian federal government. Technically speaking, this is very this has very extremely low power consumption. So that is an advantage, because we think that this SATCOM terminal can be powered entirely from renewable sources. That is battery and a portable solar panel. So during the daytime when there's sun, the portable solar panel can charge the battery, and the terminal can operate during daytime from the solar and the nighttime from the battery. So without actual electricity grid power from the grid, it may be able to run day and night using solar energy. And there's no other terminal in that world, the user terminal for fixed users, that operates like that, totally out of solar power. So hopefully that will be a massive change, because the reason New South Wales government funded this, because they want a terminal that they can take out to help with emergency services when we have natural disasters like bushfires, floods. Then those communities and the emergency service staff lose lose power and lose communications. So it's a double blackout. There's no power, power lines and a lot of things are down, and there's no communication. All the mobile base stations and the communication system is down. So communication, the SATCOM terminal that provides communications without power, without grid energy, is a massive advantage, a breakthrough in providing connectivity to those poor people, communities that are affected by natural disasters, to connect them with various government services, with their friends and families and relatives, and also the emergency services staff, including voluntary services like rural fire services, who are volunteers helping people affected by natural disasters. So that is that, but that is fair. That's very good old mechanical steering, right? So this is more about that. I already mentioned this is funding. So hopefully this will be the world's only SATCOM terminal that can operate entirely on renewable energy. And that is the first Australian-made user terminal, totally Australian-owned, Australian design, Australian manufactured in the future for the world market. And we hope to enhance emergency services and disaster management during and after natural disasters like floods and fires. That's the commercial brochure from the company that's intending to commercialize it. First for Australian use and then maybe for global market. Now there are other ways, other methods we develop. Another thing called phased array. These are for other projects. So this was done for the SmartSat project I mentioned before for inter-satellite links. So that's another way to steer the beam using phased array. Most of the steering is done by digital beam forming. So these are our partners funded by the Australian Department of Defence, but other university partners, SmartSat, Corporate Research Centre, and this is Australian company EM Solutions. This is another way to do it, but in this case, we are not beam forming using digitally beam forming. Digital means using software basically. This is using radio frequency beam forming, that is using radio frequency phase shifters. So in all these methods, for each element in the antenna, you need amplifier, in fact 2 amplifiers, power amplifier for transmission, low noise amplifier for reception, and down converters, up converters, etc., and phase shifters. That's called a beamforming chip, integrated circuit. For example, that's how the Starlink current terminal works. There is one RF channel for each element in the Starlink terminal, and the business terminal has about 4,000 antenna elements. So all these dots are antenna radiating elements, and each of them has a RF channel for transmission and RF channel for reception, including a beamforming channel for each element. So that's quite sophisticated and advanced technologies. And these are some of my collaborators making the radio frequency chips, and then meta steering that I already mentioned. We have done a lot of projects in meta steering with various partners. Most of them are funded by Australian Department of Defence. These are some of our products in the last 7 years or so. These are a lot of technical details, so I will just show you this various meta surfaces, how they look like. These are all meta surfaces. These are the meta surfaces we made with Department of Defense to make them extremely broadband. You can see that they have different colors. That's because they are all dielectric, initially 3D printed, and then we machined holes to finish the surface. We publish some of the results in open literature, like the top journals like IEEE Transactions on International Propagation, with our defense partners. 2 of them are Department of Defense, others are from UTS. These are some of the antennas with the fixed beam we developed for that. So this is the antenna, the meta surface does the beam steering. This is the fixed antenna with the fixed beam, and these are the discs that does the rotating disc that does the steering part. So got lots of different designs and implementations and publications, some rotation systems developed by the Department of Defense. And so it's a lot of technical papers, but you can find all these things in open literature, in scientific journals, if you are interested how the meta surfaces are designed, fabricated, and various features, advantages, disadvantages, etc. So to recap the advantages, I mentioned some of these already. So it works with any fixed antenna. It lacks tilting. You don't need to tilt. That means the whole package is a low profile, flat panel. You need very low operating power to operate this. And then there are other advantages like polarization, purity. It can create radio frequency waves with linear polarization, circular polarization, etc. Other efficiency figures. Some more technical details, because we don't use radio frequency chips for beam steering, like beamformer chips in this method. Because of that, there is no non-linearity, intermodulation caused by active components. Also, the active components are very lossy at high radio frequencies, 20, 30, 10 to 30 gigahertz, and they dissipate a lot of power, heat, and that can burn your terminal. So you need very sophisticated thermal management challenges in phased arrays. But here that doesn't happen. There's no loss, there's no heat. So there's no thermal management challenges, because these antennas have extremely high efficiency, very low RF loss, almost no heat generated. You can generate high power if you want. You can steer very wide band signals if you want. And there's no mechanical translations, only rotation, and you don't need very high power, expensive rotary joints or motors. You can do it with very low cost small motors. The only disadvantage is this, because of the mechanical rotation, they are not as fast as some electronically steered antennas. So but they are good for certain applications, but not the applications that you need very fast steering. So this is used by a lot of universities now everywhere, Europe, USA, Canada, Asia, from China to India, etc. Space agencies like NASA and European Space Agency have tested that, and even some Chinese defense organizations have published some work they have done, and we are working with the Australian Department of Defense Science and Technology Group to develop this further. Now this is what's happening in global industry. The Thales, that is a major defense company in France, they published this paper. They are using this method. They published in 2022 European Microwave Conference. They actually told me and briefed me about the method they said they are using our method. Actually, they mentioned it in their paper. They cited our original paper. So they made very interesting metasurfaces, entirely 3D printed. So you can see that this is, and they are using the same type of antenna. They liked our base antenna, so they made base antenna, fixed beam antenna like this for that application, for that paper. And instead of our metasurfaces, this that is partly 3D printed and we drilled holes, what they have done is they 3D printed some columns and leave in the holes, if you look carefully. So they achieve the same effect by 3D printing. So they did not have to drill holes in their technology. So otherwise it's the same thing. Then Airbus, the same company that's doing military products and also defense products as well as planes in France, they also showed a poster that has similar terminal that was displayed in 2023 UCAP exhibition booth. This is another company in Italy called Wave. They use a different base antenna with the fixed beam and put metasurfaces on it. And they gave me these slides. So they are applying this method. They call this meta lenses. The Thales and others call this deflectors. We call them metasurfaces. And we previously called them phase shifting surfaces. So there's a lot of names for this thing. Different people call them different names, but it's the same thing. It does the same job of steering the beam. And in fact, this company Wave is now making a commercial SATCOM terminal using this technology. They showed me the videos. They are using a dish reflector dish antenna as the fixed beam antenna, and then put in metasurface to steer the beam. This is another application. This is the University of California, Los Angeles. They applied this method after our publication. They extended the method for, and then another university in USA actually designed and demonstrated method. So all these things happened after our seminal paper in 2017 that basically created new area of research in antenna engineering based on this new method of beam steering. So this is our recent paper to prove that it can be applied for any type of antenna, not just the thin antennas. This is another quite different application. This is still radio frequency, but terahertz, extremely high frequency. So they are using it for near field scanning, near field focus scanning for kind of scanning applications for security, etc. This is one of the Chinese products. As I said, they made a high power version of it. They made an antenna entirely out of metal, metasurface entirely out of metal, and they claim that they can steer a very high power beam using this method. So a lot of things happened since we started. This is one of our very early rotation systems just made by some students for fun. And then the better ones were built, and then defense built some more. Now we are making more professional high-end rotation systems with experts in mechanical engineering. And so that is a lot of different areas of our research in SATCOM and other areas of beam steering. So you may ask, what is in the market, right? What is the state of the art in this area? So I'll show you a few very quickly. This is a commercial solution made by the EM Solutions, that Australian company I mentioned before. This is actually one of their early products. Now they have better products. This is a satellite communication terminal for a ship, especially for military ships. So they can keep pointing at the same satellite. For example, if it is even a geostationary satellite, because the ship has a lot of motion, especially when the sea is rough, a lot of pitch, roll, etc. So the antenna has to keep pointing at the same satellite, although the ship moves. So they develop very expensive but very clever technology with various motors and rotators. These are very expensive. The one terminal could be $500,000 or so. Very expensive, the military versions, but they are fantastic. Excellent performance. But they are tall, they need a lot of space, and expensive. So this is a terminal like that on actual ship, and this is a terminal like that on actual military vehicle. And of course, you can't conceal them. People notice that because they have to be covered by a dome like this. Because of that, it's not difficult. It is impossible to conceal, and also it's quite expensive to transport and install. Now this is a commercial version of that. OneWeb made this user terminal using that technology. Inside that is a dish antenna in each dome. So it is more like that, but it's a less expensive version, less sophisticated. This is for their low Earth orbit satellite users, OneWeb Eutelsat users. Then for aeroplanes, this is one of the cheapest antenna systems for aeroplanes to provide internet, what called in-flight connectivity. And this is fairly simple technologies made by several companies in USA, Honeywell, in Quest in Germany, Starwin in China, etc. So this is a fixed beam panel, and you tilt it around the box to steer the beam, and also you rotate it. So it's not very short. It needs certain height, and when you install this on top of a plane, you can notice a hump. If you see a plane with the hump on the top, most likely that they have one of these antennas retrofitted to provide in-flight connectivity. Then there's another technology called Chimera that is electronically steered technology, but it does not have, it's not phased array, it's a different. It has lots of switches, radio frequency switches. They have certain loss, and again, thousands of switches, and they use software to control this to steer the beam. This is one of the Chimera flat panel antennas on the top of a four-wheel drive vehicle. So you can fit it like that, and it provides satellite on the move, SOTM, while you are traveling. So these are commercial systems. Now you can buy it. They can operate with various satellite networks, OneWeb, LEO network, and some geostationary networks like Intelsat. They're quite expensive. The prices are going down, and I think they're cheaper than this now. And the original plans were very expensive per month for data, that is using geostationary satellites. Now, because they are low Earth orbit satellite constellations, they are competing with each other, and those prices are coming down to more realistic levels. This is another technology called variable inclination CTS or VICTS. This is patent from Raytheon, USA. It was commercialized by a company in USA called ThinCom. It has certain advantages and disadvantages. It's also very expensive. You need one panel like this for each band, but it is not electronically steered. It also has parts that are rotating. They need 3 rotating parts for circularly polarized each panel, not 2, and they are lot more complicated. This technology does not allow to use any antenna. It works only for a specific antenna, but it's quite good in certain areas, especially for planes. I heard that these are the most expensive antenna systems available for planes because they are very, very thin. Unlike the previous one I showed you, they are really, really thin, and hence the name thin cone, and the performance is good. So that is the technical part, and I just want a couple of slides to say about our research. We have been doing, the whole our aim is to do high quality research. So and when you do high quality research, you get good results. The experts rank our PhD thesis in the top 5% to 6%. That's quite common. We publish in the top journals, especially IEEE Transactions and other IEEE journals. We get a lot of awards and prizes, especially in the last 5 years or so. We got very large number of prizes. The publishing in good places, and all the other things are the more or less the side benefits, citations, etc., and awards and other accolades. So you can find all these things in my web page, especially UTS web page. You don't even need to remember this. If you Google my name and UTS, it will go to my UTS profile page. That is this, and from there are quite a few links to other websites. We have been collaborating with large number of organizations, government organizations, companies in Australia and overseas. These are Australian companies, these are international companies, and other organizations, government organizations, and a very large number of universities all over the world, a lot in Europe and Asia, etc. In fact, I could not put all the names here, ran out of spaces. This is only a partial list. So with all that, we were able to make some impact in industry, in government. And some of those, for example, when you got the Eureka Prize, and I think there's a lot of it went viral in Sri Lanka, so all Sri Lankans probably saw these things in national TV, etc., and national newspapers. But one of the things Australian Museum wanted me to do is to make a video that would be inspiring for example, for high school students, to encourage them to do science, STEM in general, that is science, technology, engineering, mathematics, etc. So that is that. This is a video. Unfortunately, it's not playing but you can find it in YouTube. It's a very short video. If you Google YouTube with my name, sorry, not Google, you just go to YouTube and search, put my name and search, you will find this video and few other videos that are for general audience, not much technical details, especially for younger generation, the next generation, to inspire the next generation and encourage them to more science and technology, mathematics, and make a difference to advance humanity.
And speaking on behalf of the team tonight, but he's brought the team with him, and that's how it should be in such a collaborative and engaged affair. Professor Karu Esselle from the University of Technology, Sydney. Let's give it up again for our winners.
That's a video when we received the, sorry, it's not 2021, it's 2023 Eureka Prize for Outstanding Science and Safeguarding in Australia.
Wonderful evening.
Good
evening, everyone.
From the Assistant Minister
Science
for Defense in
Science
Australia.
Always exciting.
This is also a video you can find.
Once again,
there should be a link from my profile page, and it's in few other places. These are the other major awards this year, 2024 Premier's Prize for Leadership in Innovation. That's the photo I took with the Governor General of New South Wales, and the New South Wales Minister in this area, and the husband of the Governor General. This is another one, it's another national award, 2022, Australia's National Professional Engineer of the Year. It's only one award for all engineers. So I received it from Engineers Australia. So that is basically outline of our research in this area. And as I said, we received a very large number of awards. Some of them are personal awards, some of them are group awards. But to be honest, there's nothing called personal award in this area, because alone, myself, I could not do any of these projects. I could not do any of this research. I can derive some equations by myself, but actually to get to this level, a lot of others contributed to all these achievements, all these awards. So whether it has my name or group name on the plaque, I consider all this as group awards and team awards to those who contributed. Not only those in the team who contributed to the science and technology, but all the others who supported the projects and our efforts in various ways. So I thank all who contributed to these achievements in many ways, and that is 11:24 p.m. in Sydney time. I suppose anyone who joined from Sydney is going to bed. but I'm still fine. I'm still not sleepy. So I'm happy to answer any questions if you have. But just give me 30 seconds. I will go and grab some water. Running out of a dry mouth. So then happy to think about any questions. I'll come back in 30 seconds to answer any questions.
Yeah, it was a very absolutely inspiring and encouraging session. So the only challenge is the interest of time, because professor is working in Australian time, so it's like almost nearly midnight. So we can afford a couple of questions, and he's still ready to cooperate with us.
Okay, I am back, and yes, if there are any questions, I'm happy to answer.
Yeah, thank you, Professor. So we are absolutely honored to hear from you. It was a very magnificent and informative session. So with the interest of time, we know you are working in Sydney time. It's like 5.5 hours ahead of us. So it's almost near the midnight. So still really appreciate your presence. And yeah, we can accommodate a couple of questions if audience are ready. Yeah.
Sir, can you hear me?
Yes, I can.
So when you talking about the bandwidth in satellite systems, I thought that what are the main challenges of increasing bandwidth in satellite systems?
Well, there's a system level challenges for that. That is because the bandwidth is allocated by international regulatory bodies for each system. For example, the Starlink, OneWeb, all these satellites use the same band from 10.7 to 12.7 gigahertz for downlinks, that is data coming to your terminal, and 14 to 14.5 gigahertz for uplinks for data going up. So everybody is using this, but they are in different places. So you have different antennas. When you are radiating, you have to radiate to the right satellite, right? You don't want, you should not radiate to the wrong satellite. That means you need a very narrow beam, only pointing at the satellite you are communicating with, not interfering with others. Making beams like that, to make beams like that, you need advanced antenna systems. But that is, for narrow band applications, that is not a problem. But when you need the wide bandwidth as well, then that is the challenge. So that challenge becomes part of the terminal developers problem, terminal developers headache, because your receive antenna has to have that bandwidth of 2 gigahertz to cover the entire bandwidth, and your transmitting antenna should be able to transmit in that band of 14 to 14.5. So and designing antennas and the front end is very challenging. But after that, it becomes limited bandwidth problem because the actual channel use has much limited bandwidth. In receiving is maximum 250 megahertz. So once you down convert to the channel, then your bandwidth, instantaneous bandwidth, is only 250 megahertz. So those designing those parts of the system, user terminal, don't have to worry about 2 gigahertz bandwidth, but us, the developers of the antenna system and the radio frequency front end, that includes amplifiers, beamformers, etc., achieving that kind of bandwidth is very challenging.
Right, sir. Thank you, sir. Good idea. Thank you.
Yeah, Professor, just a quick question before someone else get the opportunity from my own curiosity. So we know that antenna designing is highly involving in cybersecurity threats in these days. So in your inventions, in your product, so how we are going to address these kind of issues? Maybe you can partner with some IT and software companies, so you can get some consultation with them as well. Though have your project team are working on this area, or is it just individual project work?
So the security in these systems has physical security and cyber security. The cyber security is handled by the modem and the modem protocol, and if you want, you can add extra security to that. So we are not working in that domain. The one we addressed that when they were developing the modem, that was done by an American company called Hughes Networks, and they build in security into the modem, so you have certain level of data security. The physical security is different. That is not just security actually to protect your system by attacks by adversaries, etc. Because you are receiving signals from a very narrow beam, it's very difficult for someone to send you wrong data or tap into your wireless link. And the same, you are sending data only at the satellite you want to communicate with, so other people can't eavesdrop. Other people can't eavesdrop even if they have hardware. Suppose you have a mobile phone, right? You're talking to someone, but your antenna is transmitting that signal in all directions, not just towards the base station. It has to radiate only towards the base station because your communication, your handset talks to the base station or a Wi-Fi router, but it radiates signal everywhere. So sophisticated listener, this doesn't happen in civil space, but it can happen in the military space. Someone can eavesdrop, can get that signal and keep listening to that signal and learn your coding, learn your security code and decode it and listen to that. Because we are using pencil beams with a beam width of 2-3 degrees, or in some other applications little bit bigger but very limited beam width, and only those people, only someone who is within this beam width can eavesdrop, even if they have the best technology in the world. But we also steer our beam, right? Either we move, the satellite moves, This is not a fixed beam, so it's impossible for someone to stay within the beam long enough to learn our codes and decode it and listen. So you have, these are very secure systems in that sense. Out of all wireless systems, the systems with very narrow beams are the most secure physically. In both aspects, some adversary eavesdrop into your communication in the wireless interface, or someone trying to sabotage your receiver by sending messy signals, noise, or high power beam to basically deactivate your electronics. So that's another area we work on. Some antennas are better than others. So we are developing more antenna systems that are less vulnerable to adversary interference as a receiving system.
Yeah, thank you, Professor.
Okay, then I think there are no other questions, so it's way past my bedtime now.
Yeah.
It was very, it's my pleasure to having to speak to you. As I said, this is, now I feel that I fulfilled all my commitments to Sri Lankan engineers in this year, for this year.
Yeah. Thank you very much, Professor. It was absolutely honor and privilege for us to hear from you. We know that you are doing a fantastic, marvelous, wonderful work here in Australia, and it's a great proud for us as Sri Lankans. We are looking at you. We are watching your news. We are getting updates from you, and we know that you have a nickname called. About magnet in Australia. So that kind of intensification has been done with your work. So it was really inspiration and absolutely honor to see your progress. And the best thing is that the way you are going to inspire the young generation, allocating your valuable time for youngsters to learn from you, that is the best part of you out of everything. So thank you very much, and we are really looking forward to see you in person in Sri Lanka. Whatever the time you get, we are happy to invite you as the Institution of Engineers Sri Lanka, and we are happy to facilitate you for more programs, discussions, and we are always happy to get knowledge and experience from you. That will be something very unique privilege for us as Sri Lankans. So let me get the screen, sir, for the formalities, and let me officially thank the organizers of this event, the ISL CEO and the staff, and all the IT department staff who work behind the screen to make this session a very informative and fruitful one, and all the members who joined physically and online during this session. So thank you very much for your patience and understanding. And we knew that we had a very challenging situation in between the session, and challenges are the things that engineers are always seeking for, because engineers can convert challenges to solutions. So if you feel more challenges, that means you are going to be a very strong engineer. So thank you very much for all the professional and intelligent audience that waited for us to overcome and mitigate this challenge as well. And I again apologize from Professor for that unnecessary situation. And thank you very much for your patience and support given us to conduct this program. And we were eagerly looking forward to hear from you. And actually, we also feel that we got something very satisfactory thing before end of this year. So thank you very much for, and as yeah. as for the formality, let me share the e-token of appreciation for Professor Karu Esselle for giving a valuable insight on prospect beyond the blue planet, the space beyond opportunities, and some associated challenges. Thank you very much, sir, on behalf of IESL and the IEEE Sri Lanka section. Let me add our heartfelt gratitude and thank. This is just a break of this long discussion, and we are looking forward to collaborate with you, work with you, and get your service and support for future activities as well. And I know tomorrow will be another busy day for you. You have to work hard, and that is the only reason for me to give a break for the day. Thank you very much, sir, and it's absolute honor.
Thank you. Good evening. It was my pleasure.
Thank you very much, sir.
Bye-bye.
Bye-bye.